Good morning, everybody. Happy Wednesday. It is February the 26th today. So we are going to begin with some second law stuff today. First, just a couple of reminders. Uh, PLC 4 for Friday, that's the 28th. Homework 2 is due today. And there's a quiz posted up on Canvas. Usual deal, 1 hour time limit. That includes upload and download times. So please be aware and leave yourself a good amount of time and a reasonable internet connection, all that good stuff, and then upload your file as usual. I am almost done with grading quiz one, so that should be back at some point later this week. Um, and then we'll have lab on Friday as usual. So, other than that, I don't think there's anything procedural that's happening other than the fact that I'm trying a slightly new setup here. So we're a little bit closer to the board so that hopefully all this glare over here is a little bit reduced. And uh, I've noticed also some microphone issues. I've tried to turn the gain down on the microphone so that hopefully the ups and downs in volumes are quelled. So we'll see. Hopefully we can work towards a better transmission, a better uh filmmaking experience. Well, whatever it is, video making experience. So here's what we got today. We're gonna start up with some law two. So second law stuff, probably I would say this is up there in terms of importance of general physical laws. The set of Newton's laws, pretty good. Newton's third law is pretty important. I have to say, though, this one's above those. I unfortunately, like I've kind of been saying throughout this class, we don't really have time to delve into really the consequences and the understanding that you could gain from a reasonable exposure to this material. This is very short and time constrained. So, unfortunately, I don't feel like I can do justice to the material and give you a good look at the beauty and the power of these laws of thermodynamics. So, it's it's a little bit disheartening, but we go forwards and we do what we can. And hopefully, as time goes on, you go back and a couple of years from now, you look back and you say, oh gosh, remember we talked about that second law or that first law? I wonder what that means. What do we remember about that? So you can always go back. This stuff's always going to be around. Just come back to it. Let's talk about the second law. The second law. Now, essentially, we're done with the first law. We introduced ideal gases. We introduced ideal gas processes. We used those as a backdrop to understanding of the first law in terms of the energy conservation. So we looked at the processes. Remember that Q, the heat transferred, and W, the work done, are are both what are called process quantities or process variables. They occur during the path from initial to final. Now, the really interesting thing, or one of the really interesting things about the first law, is that it is a statement about what energy change occurs between these two states. In other words, the change in internal energy is a state variable. It depends only on where is the initial state and where is the final state. Now, the heat and the work that are transferred and done from getting to from initial to final depend on how you go from initial to final. But the internal energy does not. It's just, it's here and it's here. And if you go like this, that's one thing. If you do this, that's another heat and work. That's different heat and work. If you do this, it's different heat and work if you do that. But the internal energy change is always the same. So it actually links a state variable to two path-dependent variables. It's a very interesting idea. Anyways, we also looked at how heat is transferred via conduction, convection, and radiation. We looked at the effects of that heat on materials specific, in other words, sensible or specific heats, and latent or hidden heats and state transfers or phase changes. And now we're going on to the second law. Now, a lot of people think the second law says it's the entropy increase law, but it's not. If you really look closely at it, it's not. The entropy, which we will come to probably later today, is actually a consequence of both the first and the second laws. So let's take a look at what the second law says by itself, and then let's take a look at what happens when you combine the first with the second. And this is what I'm talking about in terms of the speed with which we have to do things. We don't get to look at the second law by itself in great detail, but we will look at the entropy because ultimately that's an important quantity, and if we have only this much time, that's one of the things we need to get to. All right, now when class started, we talked about what the second law was, and I gave you the Carnot statement of the second law. So I will reproduce that for you now at great expense of writing. So I will put this here for you. This is a cyclic process. Okay, so this is it. Make sure I got that. Yep. Okay. Sadie Carnot. First name. His first name was not Sadie. Um, he had like he had like three initials before the last name, and I think he picked Sadie. Maybe it's one of his middle names. Anyways, he was the son. He was a French science and engineering fellow, and he was the son of a rather famous French science and engineering fellow. And his father worked for Napoleon. He came along and was interested in what the efficiency of heat engines could be, because this is right when the steam engine is getting going. So this is like in the 1820s, really early on. Remember, the second law came in around then. The first law didn't come in until around the 1845, 1850s. So chronologically, these are backwards. And he says a cyclic process whose only result is to exchange heat with fewer than two heat reservoirs and produce usable work, is impossible. Now, think about how many other laws of physics do you know that use the word impossible? That's a strong word, right? That's a very strong word. I also told you about the Clausius statement of the second law. Now, Clausius was the fellow in about 1850 who said, oh, you know what? We've got a first law. We've got a second law here. This is a science. We should put these two together and go do some work on what thermodynamics is actually meaning. So this fellow was to thermodynamics essentially, if you have had 4B, he is what Maxwell was to electricity and magnetism. That's Clausius to thermodynamics. Okay, let me write the Clausius statement here. Okay, so we'll go with this. Same basic wording to start with. Make sure I get this here. Who's this to us? Okay. Reject? Yes. Reject. Now, he also uses the impossible word. This is pretty important. Impossible. Let me make sure I get the wording here. Cyclic process only results in extracting heat from one heat reservoir and reject heat to 100 from a heat reservoir and reject heat to 100 heat reservoir. Okay, so essentially, we've got two statements of the second law here by two different fellows. There is a third statement, which I will tell you about in a minute, due to Kelvin. Now, here, Clausius' statement is that a cyclic process whose only result is to extract heat from a heat reservoir and then reject it to a hotter heat reservoir is impossible. In other words, Clausius' statement is heat is unidirectional. It does not go cold to hot. In other words, the only result that this cyclic process is going to produce is taking heat out of one heat reservoir and then dumping it into a hotter heat reservoir. If that's the only thing it does, it will never happen. So this is the one directional heat flow. This is telling us that heat flows hot to cold, and if you try to make it go the other way, you can't just make it go the other way. You have to work to make it go the other way, right? In other words, the only result being that you've rejected heat to a hotter heat reservoir. It will happen if you put work into the cycle, right? So if you consume work, yes, this will happen. If you don't consume, if this cycle doesn't consume work, this will not happen. Now, we're hopefully pretty comfortable with the idea of cycles on a PV diagram. In other words, if I looked at a PV diagram and I said, I want to draw a cycle, I know that the cycle has to have a starting spot here. We'll call that 1. And then I'm going to go 1 to 2. And then I'm going to go 2 to 3. And then I'm going to go 3 to 4. And I'm going to go 4 to 1. And that's my cycle. The cycle is not so much what you have in terms of going 1, 2, 3, 4, or even if there's 4 states. Maybe there's only 3 states. Maybe there's 6 states. Who knows? The idea is you start, you go out, and then you return right to where you started. That's what a cycle means. Cycle, cyclic process, a series of interactions in which you have returned the system to its original state. Okay, now what's our system? It's the ideal gas. That means we are back at the original pressure, the original volume, the original temperature, and we still have the same number of moles of the gas. Everything's right where it was, right? So here at state 1, if I know PV, N, and T, then I go blah, 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 and I'm back to those same PV, N, and T's. Now, if I have a cycle, then what I'm going to do is when we do schematics of this, and I've showed you a few of these already, is that I'm going to denote a cyclic process with just a circle. All right, so we'll call whatever is going on PV diagram wise, whatever's happening with the motor, the engine, the whatever it is, it goes and it starts here and then it comes back, right? So it's a circle. So what this means is over here, what does this forbid? Let's talk about what this forbids. It forbids exchanges with fewer than 2 heat reservoirs producing work. So let's just sketch out a few of what is forbidden by the Carnot second law. So Carnot forbids, let's see, are we still here? We're still here. Okay, so Carnot forbids, for example, this. This is a cycle which produces usable work and exchanges heat with 0 heat reservoirs. This is forbidden. Certainly,
Okay, but remember, we know it's forbidden because of the first law. But remember, he was in the 1820s. He was 30 years before the first law came along. They didn't know what was going on. Conservation of energy, conservation of heat. Is a heat a fluid? Is heat an energy? What's going on? They don't know. So he didn't have the first law to work with. So that's why this we already know, right? But he didn't. This is forbidden. So let's a couple other ones. Something like here's a heat reservoir at a hot temperature. It's extracting some heat out. Here's my cycle, and here's the work. Okay. This is allowed by the first law, but forbidden by Carnot's second law. All right. And I realize I made these arrows slightly different lengths. I'm just trying to get them to be the same length so that if energy is conserved, right, all the cycle knows is heat came in, work came out. I can't have any internal energy change, says the system. So whatever comes in must go out. And this satisfies the first law, but it's forbidden by the second law. If I were to reverse these arrows, then sure, same idea, but still, if I think of rejecting, I'm sorry, if I think of a cycle that produces usable work, then this is also, oops, can you see that? You can't see that. And that's because I am off where I'm supposed to be. So we'll come right under here. Sorry about that. So this is, for example, TH and QH that way and work this way. Okay, now are we on here? Yes, we are. Okay, so this is what's forbidden by the Carnot cycle also. This is exchanging heat with zero heat reservoirs, and these are just one heat reservoir cycles. These are independent of one another. So there's a dotted line. All right. It's saying you gotta have two. You gotta have two heat reservoirs. A quick word about what a heat reservoir is basically something that's large and has an insignificant temperature change when heat is extracted or dumped into it, or if you say rejected into it. So the ocean, for example, a heat reservoir, okay, for small amounts of heat over small amounts of time, you will not detect a temperature change, right? A boiling cup of water into the ocean is not going to change the temperature of the thermometers that are stationed in Alaska. So, so we think of a heat reservoir as something with large thermal inertia. Okay. So these are three cycles which are forbidden by the second law. Two of which we already would have said, well, those are forbidden by the first law. But remember, he didn't have the first law. This is forbidden by the second, but allowed by the first. Right? Now, the process that's forbidden here, let me diagram that for you. Okay, so if I just dip this line underneath, we're still here. All right, so here's what's happening in this one. Here is a hotter TH. This is the hotter reservoir. Here is the cooler reservoir, TC. I'm going to try and stick with those. I'm going to try and stick with those labels, notations, hot temperature, cold temperature. And these are indicative of the reservoirs. So this is indicative of something that's hot that will remain at approximately at its temperature, and we can extract heat from it. Same deal with this. It's cold. We're dumping heat into it. It's still cold. Here is our cycle. Whatever our cyclic process is, there it is in the middle. And now we just have to say its only result is to extract heat from a reservoir and then dump it. That would be QC because it's coming out of the cold reservoir, and then dump it to a hotter heat reservoir. That would be this QH going into TH. Looks like you can just barely make that out, hopefully. All righty. This is forbidden by the Clausius second law. Okay. So things to take away from this, the use of the word impossible makes these very strong statements. And also that I don't see entropy anywhere in here. That's because the second law by itself is not a producer of the entropy idea. We need first and second for that. All right. Now, what I'd like to do is show you that these are in fact equivalent statements. Okay, so I'm going to take 5 minutes to try and uh, use these diagrams of what's forbidden and what's possible and do a couple of visual proofs to show you that these two statements are basically equivalent to each other. They sound very different, right? But they are actually equivalent to each other. This implies this, and this implies that. Now, I mentioned that there was also a Kelvin statement of the second law. The Kelvin statement of the second law is very similar to the Carnot statement for the second law. However, where Carnot says fewer than two heat reservoirs, Kelvin says one. So Kelvin would have just said one right there. That would have been the Kelvin statement. Let me make sure that I am faithful to what Kelvin said so that he does not come back and club me in the head, because that's something that Kelvin probably would do. Let me make sure here that I have a Kelvin statement. Do I have a Kelvin statement? Yes, I do. A cyclic process whose only result is to extract heat from one heat reservoir and produce work is impossible. Yes, he says one. That if you replace that with one, you have the Kelvin statement. All right, so one equals Kelvin statement. Okay. Let's go do some proving of the equivalences of these two statements here, and that means this is all done. Okay, and this is gone. This is gone. Oh, this is. Ah. All right. That's about all I can do without burning out my shoulder. Um, so let's take a look at uh, the simplest allowed heat engine from the Carnot statement. The Carnot statement says you can't have fewer than two. Fewer than two means zero or one. So let's start with two. And we're going to produce work. Excuse me. So I'm going to take these ideas and see this is what is possible from the Carnot statement here. The simplest possible heat engine. Now, could we make ones that are more complicated than this? Absolutely. It just says fewer than heat reservoirs. Sorry, simplest heat. Nope. Simplest heat engine. There we go. Now, it simply says fewer than two. So if we make two, that's basically the minimum. You want to do 3, 4, 5? Great, go ahead. But two is the minimum. So this is the simplest thing we can do. And this is the one that we're going to work with in the class most of the time. I have here a hot temperature heat reservoir, which is dumping heat, which I'm going to call QH, coming out of the hot reservoir. Here is our cycle. This is this working fluid. This is the working system, whatever this is. It's producing work. So far looks like that one, but then we have this other part here that dumps heat into a cold reservoir here. All right. So this is hotter heat reservoir. This is the cooler heat reservoir. And this is our cycle in here. All right. We're dumping heat extracted, I'm sorry, we're extracting heat from the hot reservoir, using it to perform a set of processes on a PV diagram, right? We're taking our ideal gas system from this to this to this to this to this, and we're getting work out. And in doing that cycle, we are then dumping the rest of the heat that we have left over into the cold reservoir. Now, for those of you, well, this is all of you. For those of you who don't have a heat engine to play with at home, at least one of the ones that is like a desktop model, let me diagram this out for you. Using the piston cylinder pictures that we have that we've developed. Man, this is an ornery board today. I will say that I do not have my usual pens, so I'm using these Expos. Maybe that's the problem. All right. So from a piston cylinder point of view, what does all of this cycle look like when I'm taking in heat, getting out work, and dumping more heat? So what is the piston and cylinder actually doing in this cycle? All right. So this is a demonstration or a diagram of what I have to do in the cycle in order to make this process happen. So let's start here with a piston cylinder, and we'll say, I'm going to start with, I actually want to lower that down a little bit. So we'll do that again. Let's start here. All right, so here what I have is a piston. I've got the gas is in here somewhere. Okay, so there's my gas. I am going to draw a shelf on the top of the piston just to make it a little bit easier for us to see where the work is done. Okay, so right now this is our starting piston. Maybe it's just atmospheric pressure and it's room temperature air. Okay, no problems. What I'm going to now do is I'm going to put a mass onto the shelf, right? So I'm going to increase the weight of the piston, which is then going to compress the piston or compress the gas. All right, so now I'm going to have this, and it's going to be maybe a little bit lower to here. And into this shelf, I have put a mass. Right now, my gas is compressed. If you don't like the idea of putting a whole mass on there, imagine that I smashed that up into 100,000 little tiny pieces and I did it one at a time. That would give me the ability, and we'll talk a little bit about this in a minute, to make the process of putting the mass on the piston, it would give me the ability to make that process reversible. That is a super important concept, which we'll talk about in a little while. Because if I do things quickly, then I get irreversibilities. I get things like friction in the rings between the piston and the cylinder, or I get turbulence in the gas, and energy is lost, or something like heat comes out, so stuff like that. So this is a compression. All right, we'd say that's maybe compression. What we can do now is we can, while that's going on, right, here's the gas in here. It's now going to be compressed, which means its temperature will have wanted to rise if this was the only thing that was happening. So let's say that I have a I have it in the cold bath right now. Suppose I have it in the cold bath. So I'm going to put the cold bath around here. All right, this will be my cold reservoir. And so you're going to see that heat is actually leaving during this time here. Heat's going out. Oh, you probably can't see that I just did that. Let me darken this in, make it bigger, maybe. All right, there's a heat transfer out, Q. Right, there's a Q that is now leaving the gas because it compressed, but now it's going to allow the heat to leave. Right, so the mass did work on it, and the heat is leaving. So if that cold reservoir is the same temperature as the atmosphere, say, then we've just transferred heat out. And this is an isothermal process. All right. What then happens from here to here is that I take, let's do this. Okay. I now take it out of the cold reservoir and I submerge it in the hot reservoir. All right. So heat is now going in. And this heat that's going in is causing the temperature of the gas to increase, which is causing the pressure of the gas to increase, and therefore the volume to increase. So what happens now is the gas occupies a bigger volume, and the mass. Looks like I'm gonna have to shorten this a little bit because I have an arrow here. So let me take that arrow away. Okay. Now, if I were to have been able to draw this right next to that one, then you'd know, oops, this is supposed to be blue. The mass is blue. Now the mass has increased its gravitational potential energy due to the work that the gas has done on it. Right now, I have had a large increase in the heat. I've had an input of heat. I've had an increase in the energy of the gas. That energy of the gas has done work. Some of it has done work on the mass. And also, some of it is just making the molecules fly around faster because you're going to have to put in more heat here than work is done in order to get the mass to lift and stay there because the molecules have to be moving, the gas particles have to be moving faster in order to keep the mass here at this raised height. Okay, so then I slide the mass off. Okay, so the work that has just been done is raising the mass from this level to this level, right? Now, technically, it's from where the thing starts here to up here. And this little dip doesn't really count because I get that back. So the actual usable work, right? So if I'm up here, I can just kind of do this. If I'm up here and I put the mass on and it goes, right? And now it's down here. When I put the hot bath on it, it goes, and then keeps going up. So I get whatever that little bit was here. I get that back. And therefore, the usable work really is based off where did the piston start before I put the mass on it, not after I compressed it, putting the mass on it. Okay, so here it is there. It goes up. I get gravitational potential energy in the mass. That is due to the work done by the gas. I have the heat going in. I now take, so this is, I don't know, maybe I can do something like this is where the lifted mass, so this was work, right? That's work coming out. That's the work that's been done. Trying to do something like the heat arrow here with the work arrow coming out. I don't know. All right, so now I'm gonna go back here. I slide the mass off, okay? And then what's happening is the piston is just up ever so slightly more. And now I have no mass on it. Okay. I'm keeping it at this same temperature by keeping it in the bath. Right. There's my TH bath. And now the last thing I'm going to do is go back to this first one. How am I going to do that? So it goes one, and then it goes. So if I go to one, two, three, four, like that, I'm going back to one now. How do I get the gas to get back to one? Notice what I did in the first one here. Put the cold reservoir around it. Okay. I put the cold reservoir around it. The heat comes out. So you see, I don't want to say I'm cheating a little bit, but I'm trying to put everything into one diagram where the state is, the heat is actually getting transferred on the way from here to here, right? And on the way from here to here. It's not like all happening at once. So I don't want you to get the sense that heat goes in and the mass is up, right? It's a set of steps by which, okay, I take this, I put the heat reservoir here, and then the mass goes, and you go, oh, okay. Now I'm going to slide the mass off, and it goes, and now it's over here. And now I'm going to take the heat bath off, and I'm going to put the cold bath on, and it goes, right, like this. So the cold bath basically could be the atmosphere. And the hot bath would be something like combustion and fire, whatever, right? Something to make steam, a boiler, etc. So this is a way in which, and also in doing that, I should also say, more heat is getting dumped. So see, I don't want to draw heat getting dumped right on this one, but you can see that when I take from the hot and I put the cold, this gas still has a lot of leftover internal energy that it had from the heat transfer here. And therefore that heat's going to come out. I guess I am going to draw it here because I don't have anything. I don't have a choice really. Right? There it goes. There's a little bit of heat out. Okay. So, oh, and I guess I should maybe draw something here that when I lift the mass off and the gas expands a little bit, it is going to cool off. So it will draw in a little bit more heat here. All right. So there's a heat input. There's a heat output, right? Which would be the sum of these two. The heat input is the sum of these two. And the work done is this right here. And that's how we get this thing right here. The heat input, the heat input contributes to the work done lifting, and then the leftover energy gets dumped into the cold reservoir. All right, so that's kind of what it looks like. If I were to think of this as a internal combustion gasoline engine, what I would think of as the cold reservoir is basically the atmosphere. The piston goes down, draws in all of the cold air from outside, relatively cold air compared to the motor, right? It then compresses, which means it's going to heat the gas quite a lot. It does that adiabatically because it's a really quick compression. The spark goes off, which causes a large heat input, which drives the piston down. That's where the work gets done, right? And then the piston goes back up again, shoots all of the bad exhaust gas out into, oh, who knows where? No, nobody cares about that stuff. We'll just dump it out the tailpipe and into the atmosphere, and then draws in a new set, and off it goes. It's not a it's not a simple PV diagram, but if I just kind of say, well, blah 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 blah, it's kind of like that, then maybe I can convince you it kind of is like that. It's a little more complicated than this, but nonetheless, it's on the same order of magnitude. Okay. So that's what an engine looks like, right? It's doing these steps approximately. Not every, well, we'll get into this more later. I just need to stop with this. There are many different cycles. This is just an example. This is not always the way it is. It's just kind of a way you could think about it. All right. So we'll go through a series of of different cycles later. Okay, now what I want to do is go do the showing of these. Oh, by the way, before I do that, before I do the showing, I've been talking about this. What I want to do is also I'll alert you to one other fact. Um, Maybe I can use this diagram right here. A heat engine. What is the purpose of a heat engine? It's this. The purpose of the heat engine is work. I want the heat engine to do work for me. I don't want to do the work. Make it do the work. Okay. Give me the workout. That's what I want. Okay. If I thought of completely reversing every single one of these arrows, in other words, uh, well, you know what? I don't need to do this. So you have hopefully written this down, and if not, well then you can go back and look at it later. Okay. Now, suppose that I reversed every one of these arrows that way, and that way. Now, what do I have? This is no longer a heat engine. I'm going to erase this. This is no longer a heat engine. This is a refrigerator. Right? The simplest heat engine and the simplest refrigerator are basically just opposites of one another. The point of the heat engine is to extract work, and you do that based on temperature differences between the hot and cold reservoirs. The point of the refrigerator is to make the cold thing stay cold. That means I need to extract heat from it. And in order to extract heat from it, according to Clausius, I can't do this. I can't extract heat from it and then dump it out. I can't have my refrigerator just take heat from the inside cold compartment and dump it out into the air in my house. Can't do that. I have to put work in order to make that process happen. Therefore, I have to plug the refrigerator in and take electrical work in order to run this compressor, which takes heat out of the cold space and then shoves it out into the air in the room. All right. So in that case, the hot reservoir is now the atmosphere. Whereas in the engine cycle, it is often the cold reservoir is the atmosphere. Here, this is something that's typically colder than the atmosphere. You want to preserve the coolness of this interior space and then reject that heat into the air. So this is a refrigerator, and it's the simplest possible one. Now, let's go through and I'll give you a taste of how to show that those two statements are equivalent. Okay. And that means that we are going to do this. Oh, it's just brutal. Well, it's not brutal. It's just too much erasing. All right, so this is going to be falling under the heading of equivalence of the Carnot and Clausius statements. Equivalence of Carnot and Clausius. That's funny. Okay, like so. All right. So what we're going to do is we're going to take a tack of contraposition like we did in the first law one. I'm going to assume something that is explicitly forbidden and then show that if I combine that with a couple of allowed things, the result is forbidden because one of the originals was forbidden. I'm going to start with the idea of a Clausius, I don't know if I say the Clausius refrigerator, but imagine that I started with a refrigerator like I just erased here. Okay, I've got a TH here, my hot reservoir, I've got my cycle, I've got my T cold here, and I have a QC going here, a QH going there, and I have to put work in order to make this happen. Okay, so here's the work going in, and this is allowed by everybody, right? This is allowed. That's an allowed Carnot, and it's an allowed, well, it's mostly a Clausius. Now, what I'm going to do is I'm going to take a disallowed by Carnot, a disallowed cycle, which produces work. I'll just say it produces work W prime here. All right. So that this is clearly forbidden. And I'm going to take a forbidden plus an allowed and see what do I get. If I were able to have a cycle which produced work without exchanging heat with any heat reservoirs, this is the good old zero, the zero transfer of heat in order to produce work. What I'm going to get now is if I kind of add these two things together, I'm going to go plus like this, and I'm going to go equals. And what I'm going to do is I'm going to evaluate this. Actually, I'm going to scoot my equal sign over a little bit, but not like that. Okay, I'm going to scoot this over. I'm going to evaluate this at work equal to work prime. Now, that means that if I say that the work prime, which I am extracting from this, I don't know how you would do that, but I'm extracting work prime from here, and that happens to be exactly what I want in order to run this refrigerator. So I can run a cycle with no other effect other than to produce work and put that work into the refrigerator. The refrigerator needs work in order to make this heat transfer go up. And so what would happen now is if I take these two things together, if I like combine the 1 and 2, if I call this 1 and 2, this is 1 plus 2. Oh, so shouldn't it just be 3? Yeah, probably should be. Here's my TC, here's my TH. And that means QC goes this way, QH goes that way. These two are not affected. Okay, these are exactly as they are because there's no QH and QC over on this side. And therefore, if I take something that's not allowed and I use it to power something that is allowed, I'm going to get something that's not allowed. And this is specifically this is the exact thing that Clausius forbids. So the idea that I've taken something from Carnot and I've taken a forbidden and allowed, and I've said, okay, look, if I take something that contradicts the Carnot second law, I'm going to get something that contradicts the Clausius second law. Therefore, they are equivalent. So we get this. And this is a lot of thermodynamics right here, is just, okay, what's possible? Is this allowed? Is this not allowed? I know I've talked about this before when we did it with the first law thing. Okay, so this is one way in which Carnot and Clausius are equivalent. Now, is this the only thing that's forbidden by the Carnot cycle? No. Or the Carnot second law? No. There are other situations forbidden by the Carnot second law, and you can go in and try to mess around with those to see if you can produce this, because if you can produce this, then it's equivalent, right? What you're shooting to get is something that violates the Clausius second law. Okay, now what I want to do is do the opposite. So what I'm going to say here is that I've showed you one thing, and I've showed you how Carnot and Clausius are equivalent. So for this one case, and so I'm just going to go on and say, there are a lot of other cases. I encourage you to look at some of them and try some of them out, and I will give you the opportunity to do so on the homework. But nonetheless, this is kind of the mode of establishment of the equivalence of the two, right? So now this is showing that Carnot is equivalent to Clausius. Now, I've showed that if I violated the Carnot second law, then it leads to a violation of the Clausius second law. What if I take a violation of the Clausius second law, and can I show it leads to a violation of the Carnot second law? And that's how you're going to prove that this is equivalent to that, and this is equivalent to that. All right. So if I show that they're both equivalent to each other, then they're totally equivalent. All right. So what I'm going to do here is I'm going to start off same idea, contraposition. So I'm going to start off with something forbidden. And this is the only thing forbidden by the Clausius second law. So let's just draw that in. It's this thing, right? Like so. This is forbid. That's the thing that Clausius specifically forbids in the second law. So now let's just combine that forbidden thing with an allowed thing. Okay, so now this is the allowed, and this is an allowed Carnot heat engine. Alrighty, so I'm going to take this here, we're going to do this, and we're going to do this, and I'm going to dump that into there, and that into there, and this is QH, and this is QC, and this W comes out like that. Okay, now I think you can see what I'm about to do. Here is something forbidden by the Clausius second law. Here is something allowed that's allowed by the Clausius and Carnot second law. Can I now show that this leads to something forbidden by the Carnot second law? Well, if I evaluate these two here, I'm going to evaluate these at Q. I should probably call one of them prime and one of them unprime. So let's just call the Clausius forbidden ones. I'll call those the primes because that's what I did on the first one, right? Yeah. So the forbidden thing has the primes on it. Now what I'm going to do is I'm going to evaluate this at QC prime equal to QC. If I do that, when I combine the two things, then I'm going to get some effective QH that has either been transferred in or out, right? And the arrow direction would depend on which one is bigger, but nonetheless, that leads to two different violations of Carnot's second law. Because what have I done? There's no work involved in engine number or in situation number one here. So all the work is coming from situation two, and that's coming out of the cycle. No heat is getting dumped into this reservoir. So it's an exchange with a single heat reservoir and work is being produced. And that violates Carnot's second law because that's an exchange of heat with less or fewer than two heat reservoirs, right? That's an exchange of heat only with this one. I've eliminated this one. And therefore that violates Carnot's second law. So here I can show you the equivalence between the Clausius and the Carnot. And here's the equivalence between the Carnot and the Clausius. So we say they're equivalent. All righty. Now, it's a pretty funny thing because these statements carry such huge consequences. They are numerous and far-reaching. And that's why the verbal statements of these things are kind of so long and winding to traverse here. But nonetheless, if you follow them through, then you can ultimately do things like this, which shows that, oh, can I do this? Can I not do this? If I assume that the wrong thing is here, is that the right thing over here? Is that a right thing or a wrong thing? So it's this process is a lot of classical thermodynamics. And I think that that it just doesn't get showed and it doesn't get it doesn't get demonstrated. It's just instead we have only a few weeks to talk about thermodynamics, so we have to just hit the mountains, and that means things like entropy. Okay, I want to talk about reversibility now. All right. So Clausius combined the first law and the second law to create the science of thermodynamics, and he went further. And Carnot kind of was the one who came up with this type of setup. And so Clausius took that and he went one step further and he said, well, we need to make these reversible. So I want to talk for a minute about reversibility in a heat engine or really in a process. And what does that mean? I've skipped around this a little bit on the way to this point by saying that we should do things reversibly. But what does that actually mean? So I need that. Let's talk about the concept of reversibility. Okay. Let's talk about the concept of reversibility. Um, so there are lots of processes that are naturally uh, kind of like one direction, right? Heat flows one direction. Uh, we get work from doing particular, we get the work out when we do this particular thing, or we have to put work in order to make this happen. Um, but we don't observe the opposite, right? We think about heat flowing, but not seeing heat, or heat flowing hot to cold, but not seeing heat flow cold hot unless we make it happen, right? So a lot of processes uh that we use, and you can think specifically about the ideal gas processes that we have looked at. We've looked at isobaric, isovolumetric, isothermal, and adiabatic. Those four processes. Now, anytime we're able to sketch them on a PV graph, what has happened, for example, just take an isobar here, 1 to 2, like this. What has happened is that I have been able to, at every point, say that the system had definite pressure, volume, and temperature values. Okay. In other words, I let the system come to equilibrium at every small change so that I could then measure, right? This is all kind of a thought experiment, so that I could measure the pressure, volume, temperature and say, okay, and I can make that dot right there. So really, when we draw a process on a PV diagram like this, what is it really? It's really a situation where we have tried to make small changes. Imagine doing this experimentally. I'm going to take a small, like I took that mass and I cut it up into like 10 different pieces. I put a little mass bit on there and it would compress and a little bit of heat would come out. So I'd have to measure the temperature of the water now and deduce how much heat came out. And then I'd put the next piece of mass on, it would compress slightly more, and then I'd have to deduce, all right? So in other words, what I'm doing as I'm going along a process like this is I'm really doing this. I'm going to successive equilibrium states like that. Uh, yeah. So it's a bunch of dots. And now, since experimentally we can't do this, now the theorists take over and say, okay, let's just make the distance between successive equilibrium states smaller and smaller and smaller, and let's just make them differentially small. When we make them differentially small, now we've got a line that we can draw, and this is a nice continuous thing that we can deal with. Okay. Because theorists, we don't get our hands dirty. We do things clean. This is okay, a nice easy line. It's not a set of dots, especially because in experiment, you get the dots are going to be going up and down because there's uncertainty, and then you go, oh, I got a curve fit this thing. Nah, nice, right? That's a theorist view of things right there. Um, so what does it mean to be reversible? What it means to be reversible is I have taken the masses, put them on, right? And the thing has compressed. And I've gone from state 1 to 2. Well, compression. Okay, so wrong thing to say because we're going here clearly as an expansion. So okay, but let me use it as an example. We put the masses on the piston sinks, put a little bit more on piston sinks, put a little more on piston sinks, and now I take one of them off, piston goes back, I measure the temperature. It was what it was on the way in. I take the next piece of mass off, boop, piston comes up. The temperature and pressure and volume of the gas, all what it was when I put the mass on and it sank down. I take the mass off, it comes back up, I measure them, they're exactly what they were. So what this means is I can take a process from 1 to 2, right? And I can think about all the equilibrium states that I have reached in there. And of course, for a theorist, it's an infinite number because that's what we do. And then I can, because I was so careful, I can reach state 2, I can turn around, undo everything, and go straight back to state 1. Well, not straight. I got to do everything differentially, incrementally, right? So it's just a little bit of change, a little bit of change, a little bit of change, and then I go all the way back. All right. So if I can go this way, reach state 2, and then I'm going to draw it underneath so you can see it. If I can go all the way back that way, then it's reversible, right? It's reversible. I can go directly along the same exact path. All right. Which means that we have to think of the system coming to equilibrium with every small differential change. With or slash after every change. Such that undoing those changes puts the system back in its original state. That's the key part, right? And I'll put original state variables here. In other words, I can measure PVT. I'm assuming N is constant. I can measure the PV and T, and I can see, yeah, these are exactly the same as they were when I started. And that's because I was so careful, because I just did a little tiny change and then a little tiny change, and I undid the little tiny change and I undid the other little tiny change, and I'm back to where I started. Great. That means I haven't lost anything. I haven't lost anything to sliding friction, right? Because friction is going to take and it's never going to get back. And I haven't lost anything to turbulence or viscosity. Those take, they never give back. All right. So this has to be a pretty careful process. And that's why we're theorists, because we can imagine really careful processes. And then the experimentalists have to go do them and they fail. But you know what? We never do, because we can imagine perfect processes. So, so, uh, if you have to, if you are convinced, if you have to imagine perfect processes in order for things to get done, then you are probably on your way to theoretical physics. All right. So it's a situation where we are infinitesimally changing the state of the system with no imperfections, no losses, no nothing, such that we can then undo those changes and restore the system. Why is this important? I will add to this here. This incurs no losses. Okay, so there's no losses. Why is this important? This gives us the ability to calculate and explore essentially what is the best possible scenario that we can come up to. um, I guess I could say engine, or I could say cycle on a cycle's performance. Okay. In other words, we have now, by eliminating losses, we have now been able to say this is the absolute best that anyone anywhere could ever do. There's nothing better than you can do than this. If you have a reversible heat engine or a reversible refrigerator, you're running it off a reversible cycle, then you are at the pinnacle of thermodynamic work, right? You have done the best job that you could possibly do, and no one will ever do better than that, right? There's simply no way that you could do better than not losing anything. I haven't lost one thing, not even a little bit, not one thing. And therefore, that gives us the upper limit on how well we could possibly do. All right. This is the best possible scenario. Therefore, every real situation is going to be worse than what we're doing here. Okay. And that kind of mentality is essentially the basis of thermodynamics. It is, at its heart, very depressing because we'll come up with the best case scenario and know that we could never approach that. We can't ever reach this, and also we can really never approach it because we just do things too quickly. Okay? Think about this. There may be work, right? Suppose I did a cycle and I went up and out and around and back, and I had a cycle performed here, and it's reversible. So I definitely got work out, right? I extracted work from the cycle, and I dumped the heat and did the heat reservoir things, and I obeyed Carnot's, and everything's wonderful and dandy. But the question is, imagine of that work that came out, what was the power of the work? In other words, what was the rate of delivery of the work if I'm doing something in a reversible manner here? How quickly is that work coming out? Quickly or not quickly? Yeah, so the power basically, when you're talking about a reversible cycle, the power is basically zero because every step is infinitesimally small and you wait a really long time for it to establish equilibrium. So, yes, you get the workout, but it takes ages to get there. We don't have that time to waste, so we do things irreversibly. Essentially, every process that we have ever built in order to be an engine or a refrigerator to help assist us is irreversible, essentially. I just eliminate the word essentially. Every single process we've ever done is irreversible because we cannot eliminate all the losses. It's just not possible for us to do that. That's why this is kind of an important thing for us because this tells us the absolute best that we could possibly do. And we can try to shoot for it, but we know we're never going to get there, right? It's just not going to happen. Okay, so we have an upper limit established, and we can talk a little bit about efficiency at this point. And I want to talk about a couple of theorems. Say, I want to give you a couple of theorems, and I want to talk about efficiency. So let's take this out. Actually, you know what? Actually, you know what? I'm gonna do that. I'm gonna leave that to tomorrow. You know what? I'm gonna do that later. What I'm gonna do is what I'm gonna do is I think I'm gonna yeah, this is what I'm gonna do. I'm gonna skip ahead a little bit. I am gonna talk a little bit about entropy today because I realize the PLC has a lot of entropy on it. So we are gonna do a little bit of entropy. All right. So I'll come back to a little bit of the discussion of reversibility and efficiency. We'll come back to that tomorrow. But in order to get you started on the PLC, let me talk about entropy now. Okay. It's a long and winding road about how entropy was established. I mentioned before, it's a consequence of both first law and second law. It's not second law alone. So when you look at the combining of the two laws, it turns out that this quantity continues to pop its head up and say, "Hey, I'm something of importance." All right. So the entropy is essentially, interestingly, it was named to be close to energy just like enthalpy was close to be named, is close named to energy. They're all kind of closely named. But the idea of the entropy is and this is by the way a slightly this is a slightly modern take. This is not strictly classical, but it's essentially a measure of the disorder of the system. All right. And so the question you might ask yourself is, well, okay, how do you how do you make disorder in a system? How does disorder come about? Well, I'll tell you, it's when heat's transferred. When heat is transferred, things get more disordered. Why? Well, what's happening? If I think of my ideal gas as the system and I dump a bunch of heat into it and I say fix the volume so I don't let it do any work. I just say, here, this is a gas. It's contained in this rigid box, and I'm going to put a flame underneath it, and right, and I'm going to heat it up. What happens? They become even more disordered, right? If I take the heat away and I put them in ice, they get slightly less disordered, right? And if I put them in liquid nitrogen, then they get slightly less disordered. And at some point, you can kind of imagine that you could reach a situation where that you have the minimum amount of disorder possible, right? So everything's nice and stacked squarely and perfectly, and it looks like a museum quality type of thing, right? So the entropy of the entropy of the system increases, right? Or to say the disorder increases when heat is added. And it subsequently decreases when heat is removed. Okay. Now, the definition to this is that the change in the entropy, delta S, okay, is basically defined to be at what temperature did you dump all this heat into it, right? So I got to take those and add them up. I take these DQs, heat transfers. At what temperature did I transfer the heat? And I add all these little heat transfers up, and I get that that's how much the entropy changed. Okay. I'm just writing heat transferred here, but I should be careful because there is a DQ here, so it's really small amount of heat transferred. And so I'll put small right there. It's not the entire thing, it's just how much it is. So for example, imagine that you had a sensible heat transfer. I have water and I'm heating it up. Now the temperature of the water is increasing. That means I'm putting heat into it in order to get the temperature to go up. How am I putting heat into it? Well, if it's a sensible heat, then the heat that I'm putting in order to affect uh, a macroscopic temperature change, we already know is mc times delta T. Therefore, if I differentialize this thing, I just take a small bit of heat, and that causes a small temperature increase. And now I have the ability to go, oh, look, I can do something interesting here, right? So if it's a sensible heat transfer and you want to know how much did the entropy change during this temperature increase, then I would say that the delta S would be from T initial to T final of mc dt over T. And you're going to notice that you're going to get a log out of this. Right? So thinking about how entropy is generated is based around what heat was transferred. So if you can get your hands on a A mathematical form of how the heat was transferred, great. If you have to go to a PV diagram and use the first law, great. By hook or by crook, you figure this out. Okay. And that's part of what the first law is about. I'm sorry, that's part of what the PLC is about this week is looking at which ones of these processes is going to generate more entropy? Well, you have to think about the heat transferred. All right. Now, if it's done at constant temperature, you can see that the T can come out of the equation, out of the integration, and I would just get integral of dq, which means it's just the Q, right? So at constant temperature, I'd get that. All right. So a little bit of an introduction to entropy. Hopefully, we'll have some time tomorrow to talk about how this got to be, but I felt like I didn't want to run you up against the clock like I did last week. So a little bit of a start on getting PLC stuff done so that you have it to go forwards. Take a look at some of that. Remember to hit the quiz today, submit your homework today, and after that, then I think you're at least free and clear until Friday when we'll have, or whenever you do the labs, and we'll have that going. So I will say good day to you. Have a great rest of your day. Try to think about how much entropy you're increasing in the universe here by your just very existence. Happy rest of your day, folks, and we'll see you next time.